Now, because of their significant ring strain, epoxides have great synthetic utility as intermediates. An epoxide is a great way to add two carbons in between an OH group, okay, and another carbon. And we know that we can use different reagents to open up epoxides. These include HBr, acid, dilute acid, right? Now, if you want to alter the carbon skeleton, then all you need to use is a Grignard. You can use a Grignard, or you can use an acetylide. So here you have a Grignard, and here you have an acetylide. Anion. Okay. Now, strong nucleophiles will react with epoxides, and they do so via an SN2 mechanism, as you can see here. This is not new. This is something that you already know. If you use a hydroxy, then you get a 1,2-diol. Okay. The reaction, of course, will favor the products. As you can see, remember the epoxide is very strained, so it's going to open up under any slight attack of a nucleophile. And this is what is happening here. Now, in general, we know that alkoxides are not good living groups, okay? But because with the significant strain that is associated with the epoxide, upon attack of the nucleophile, the epoxide ring could easily open, okay, because of the significant strain. Now, if you look at this energy diagram here, you can see that the ring opening of an epoxide, right, is to give the alkoxide is exothermic. You can see here it's exothermic. Delta H is less than 0. Okay, that's for the epoxide. On the other hand, the formation of an epoxide from, say, an ether is endothermic. Okay, so if you are going to start out with an ether, okay, and you make this react with, say, a hydroxide ion, right, this is a very endothermic reaction, because even though you get your alkoxide and the formation of the alcohol, okay, this is a very endothermic reaction, because if you try to do something like this, where the attack occurs like this, right, then you get the alkoxide, which is a bad living group. See, this is a bad living group. See, the only way you can get it to open up is if you are dealing with an epoxide, and the reason why the epoxide reaction is more kinetically and thermodynamically favored is because, of course, it produces through a smaller activation energy, as well as it produces a more stable product. See, as you can see, the reaction is exothermic in this case. Now, epoxides can be opened by many other strong nucleophiles. Like if you started out with an alkoxide, or maybe a cyanide, or a hydrogen sulfide, or a Grignard, or you can easily use a simple hydride. Or if you use acid, then you can easily open up the epoxide to give you the bromohydrin. Now, both radioselectivity and stereoselectivity must be considered. Okay. Now, given that the epoxide ring opening is SN2, okay, predict the outcome of the following reaction. Now, in the presence of a good nucleophile, right, you can see that the nucleophile goes to the less hindered. See, it goes to the next hinder. That's because the reaction proceeds via SN2. You see, here it's tertiary and here is primary. So the reaction, the nucleophile goes to the less hindered primary carbon. Okay, and that's how you have your ring open, and you can see again that the orientation of the nucleophile and the hydroxy is an anti-addition. So it's an anti-addition. So it's very important that you note the stereochemistry. The stereochemistry is anti, right? Why that regiochemistry is going to the less hindered carbon. As you can see, this is primary carbon, while this is tertiary carbon. You see, so because the reaction goes via SN2, right, we expect that the nucleophile is going to attack the less hindered carbon. Okay, so that's what we expect. Okay, now if the reaction were to go under acidic conditions, then you can see here that the epoxide can be protonated, and once the epoxide is protonated, this becomes an excellent leaving group. The hydronium or the oxonium cation becomes an excellent leaving group. So the attack of the nucleophile leads to the formation of this halohydrine. As you can see that. Okay, but just remember, whether you go under acidic conditions or under basic conditions, the reaction always goes SN2. Okay, now let's keep moving. Now, water or an alcohol can also be used as the nucleophile under acidic conditions. So in this case, you get the 1,2-diol if you use water in the presence of acid. While if you use an acid in the presence of an alcohol, then what you get is a beta hydroxy ether. Okay, because now you have, this has alpha beta, so you get a beta hydroxy ether. Okay, that's basically what happens. Okay, now in antifreeze, ethylene glycol can be made this way. Okay, now let's talk about the ring opening of epoxide. This is very important. Now propose an explanation for the following regiochemical observation. You know, of course, we got to consider steric and electrolytic effects. Okay, now remember I said that because the reaction, the ring opening of epoxides goes through an SN2 reaction, we expect that the nucleophile will attack the less hindered carbon. The nucleophile attacks the less hindered carbon. Okay, now that's what we expect, but there is actually an exception here. Let's say there's an exception, because in the presence of acid, when you have a tertiary carbon, the nucleophile attacks at this tertiary and not at the primary. Okay, and the reason is because the tertiary carbon has an electron releasing effect. So any positive dipole that develops is stabilized by the electron donating effect of the alkyl groups. Now we know that that's beginning to sound like an SN1. Okay, because if the nucleophile preferentially attacks the tertiary carbon under acidic conditions, that cannot be SN2. It's going to be SN1. However, the observations in this mechanism is likely SN2, right? Because there is inversion of configuration. There is inversion of the configuration. You see? Because if it were SN1, then you should have a racemic mixture. But in this case, you have inversion of configuration, right? Now, this is the only exception you're going to encounter. Every time you have a tertiary carbon in an epoxide in which acid promotes the ring opening, the reaction will go SN2, but the nucleophile is going to attack the tertiary carbon and not the primary carbon. Now that's only if you have a tertiary carbon, right, and the reaction is promoted by acid. Okay, see, if the carbon was secondary, the nucleophile will go to the less hindered. You see, to go to the less hindered. But in the case that it's tertiary, the nucleophile goes to the tertiary carbon. But this is only when the reaction is acid promoted. So when the nucleophile attacks the tertiary center of the epoxide, the intermediate takes on some carbocation character, but not completely. Okay, it takes on some carbocation character. I can see because of the electron releasing effect of these carbons, these three carbons, we know that there's going to be significant stabilization of this partial positive charge. And because of the significant stabilization of the partial dipole, we expect that the nucleophile will want to attack through that end. Okay, nucleophile will want to attack through that end. Okay, so just make a note of that. Now, sulfur appears just under oxygen on the periodic table. Now, sulfur appears in thiols, right, as in hydrogens, like a thiol group, analogous to an OH group in the alcohols. The name of a compound with an SH group simply means thiol rather than ol. So all you need to do is take away the E of the alkane and replace it with ol in the case of the alcohol. But in the case of the thiol, because the E and the T, E is not a vowel, you have to keep it there. Okay, so in this case, this becomes 3-methyl-1-butane thiol. Okay, note that, it's very important. Okay, now thiols are also known as mercaptans. An SH group can also be named as a part of a side group rather than part of the parent chain. Okay, right, so in this case, this is called, in a side group is called a mercaptal or a mercaptan. And the reason why it is called a mercaptal is because mercury is used, and it can be treated using 1,2,3-dimercaptal 1-propanol. Okay, so if you have something like this, you can use it to treat mercury. So if you have a mercury spill, the mercury spill can be cleaned up by using the 2,3-dimercaptal 1-propanol. Okay, you can use it to treat mercury, you can use it to clean up the spill. And that's the structure right here. Okay, now thiols are known for their unpleasant odors. By now you should know that sulfur stinks. Just like if you use like an sulfur ointment to treat like eczema, it really stinks. Okay, and this thiols is what the skunks use as a defense mechanism. That's why the skunks really stink really bad. Now, methane thiol is added to natural gas, methane, okay, to detect gas leaks. And that's because ordinarily methane is odorless. So how would you know if you had a gas leak in your home if you are dealing with an odorless gas? The best way to do it is by introducing a pungent smelling gas like methane thiol. It contains sulfur, and so when there's a gas leak, you smell something like sulfur. It's just the trace of methane thiol that is in that has been introduced into natural gas to be able to detect